Welcome to Radio Frequency IC Design class, and this is your lecture 7 in Unit 2. And in today's class, we will continue our discussion on RF systems. Today, we will look at something called as dual down conversion receiver, and also we'll start with we'll get introduced to something called as image reject receivers. So just to have a recap at what we have done in the previous class, uh, we understood heterodyne receiving, or the process of mixing or heterodyning. And in last class, we saw there are two ways we can actually do this heterodyning. One is constant LO and another one is constant IF heterodyning. And we also stated that to simplify the baseband receiver path, we usually go for constant IF down conversion. And then we saw something very specific to this image reject receivers. This heterodyne receiver is called image, the problem of image. So the frequency component, which is equidistant from the LO, uh, is the same equidistant in the sense the difference between the LO and omega in is identified as the intermediate frequency, the difference between. So if there is a signal present with the same difference towards the other side of the spectrum, definitely that also will be down converted and will be uh, located to the same center frequency. By that our desired signal may get corrupted. So that is called as image problem. And depending on where we do this injection, or where depending on the location of this LO with respect to input frequency, there are two types of injection: high side and low side injection. And so after understanding what is image problem, we sort of introduced a solution to image problem, that is actually to suppress image. We can actually introduce a filter before the mixer. Then we saw that if I'm introducing a filter before mixer, we have to operate at the same high frequency. So that will have again constraints on the filter characteristics. So to make that ease, one thing we can do is, if I can keep omega if very large, we can easily realize this filter of this cara, and thereby we can eliminate the image, right? But then we understood that there is a trade-off. So to maximize image rejection, we have to keep omega f very large, so the 2 omega f will be far away, and we can actually get a very relaxed filter to remove the images. But this was in turn posing another challenge in actually the idea of heterodyning itself, right? Because the whole idea is to do channel selection is what we are doing, this heterodyning process or this mixing process. Now if I'm trying to keep omega f so large, that will not help in channel selection at all. So we saw that there is actually a trade-off between what we call as this image rejection and channel selection, right? So then we stated that yes, we have to do this, we have to take up this. How it is, probably I did not okay, let me just draw the diagram over there. Mm, yeah, so how we go about now is, we have this antenna, and then we have the first filter, which is in fact selecting a band, which is band pass filter, followed by the amplifier, low noise amplifier. That will be followed by the filter, what we call as image reject filter. And after that, we'll have this mixing operation, then followed by another filter, which is a channel uh, select filter. So this is the yeah, this is the architecture so far, right? Now if you look at these two filters, if I focus to image reject and channel select filters, for image reject filter, omega IF should be high. That is a requirement of this image reject filter to have a very relaxed filter. But for channel select filter, this omega IF should be low. So that means we can clearly see that there is a trade-off here. And now we'll see how we can deal with this trade-off, right? So here you can see the requirement is actually a high IF, right? or this high IF is making this image rejection possible. Yeah, here also the IF is high. That is why channel select filter is not able to filter out the interference very close to the desired signal, right? Similarly, if you look at the second case here, the IF is low, so that the image reject filter is not able to reject images properly, but the channel select filter is able to reject the interference very close to the channel, right? I hope this is clear. So for any questions from this, if you have questions, please post in the chat box. We will definitely discuss. Right. So I'll be continuing from here. So we understood that there is a trade-off between this image rejection and channel selection. And now the question is how to solve this problem, or as we understood that there is a trade-off between image rejection and channel selection, how do we go about now? So that is what we will do today. So our idea is actually seeking for a solution to resolve what we call as this image rejection and channel selection trade-off. Solution to resolve image rejection and channel selection trade-off. So do you have any solutions, or do you have any thoughts on this? Now we understand that we have to use an image reject filter, and then we have to use a channel select filter, but there is a trade-off. So how do we go about? So what can be one simple solution actually to do this image rejection and channel selection properly? Maybe create a sharp filter. Yes, Anirudh, yes, but that is a point, right? The problem lies actually there. To get or to rely on the characteristics of a filter, right? So if we had that option, we would have done directly at the beginning itself, right? To remove the interference. So yes, no problem, no problem. And yeah, what you suggested is right. We should actually use a filter, but that is not somehow it is not possible for us to realize a filter and to get especially for IC implementation is it is slightly difficult. All right, Abhinav, can you just elaborate on that? Resonance means what are you planning?
Maybe we can come up with a circuit which might resonate particular
Hmm.
frequency.
Hmm.
So we need not develop two separate filters. Resonance
Uh,
is much better compared to a filter.
yes. So now when we say about resonance, again we have to yeah, definitely we have to use some RLC components there, right?
Yeah.
Either you should use an L, yeah, to resonate you will definitely have need this LC components, right? Okay, so resonating is, see, our need is actually to filter out, or to to reduce the frequency to a lower one. That is our present need. So how that can be addressed? I just want you to think with us in the same line, because alternate solutions will be there. I'm just trying to address with this within the heterodyne atmosphere itself. We are doing heterodyning process. We have something called as image rejection, and we do have something called as channel selection. Now, if you look at the problem is for image rejection, omega IF should be very high, and for channel selection, omega IF should be low. And that is where we saw the trade-off. Now, if I want to go about with the same kind of architecture, what extra modification we can do? All right. Can we down convert omega IF after image rejection? Yes, that is what we want to do, right? After image rejection, we definitely, yes, we want to down convert. Yes. Shifter kind of thing, maybe. I didn't understand that, Akshay. Filter, sorry, shifter, I didn't understand. In fact, we are actually doing a frequency translation itself. Yes. All right. So Two-stage shifting. All right. Yes, two-stage. Probably Nagraj also was mentioning something like that. I don't know. Yes, we have to use a local oscillator. Yes. So the idea here is we are going to extend this idea of heterodyning. Right. The key point here is the extension of this heterodyning process. So what do you mean by extension of this heterodyning? Heterodyning is actually the process of mixing. So when I say I am extending this heterodyning, that is pointing to a condition where I am actually introducing multiple down conversions. Multiple down conversion. So that is actually giving you this new architecture, what I mentioned here as dual down conversion, or we call it as dual IF heterodyne receiver. So let me explain how we do that. So we have the component coming in, and we use something called as a band pass filter, that is to select the band at the first. Then we follow that with an LNA. So let me number this. This is band pass filter 1. Now I use another band pass filter. I call it as band pass filter 2. If I write the role of each band pass filter, this is actually to select the band, and this is basically to reject the image reject filter. And now that should be followed by what we have the previous same stage. So what I'm drawing here is same as what I have drawn in this previous slide, right? Till channel select filter, that remains same. So I will have a mixer here, and I will be actually employing a band pass filter here, right? So now you can see that previously what we have done is we have a band select filter at the front end, followed by we have an LNA. Then we had this image reject filter. Now this image reject filter image reject filter is helping you to reject the images. But if you see the image the filter there, or the center frequency is not yet changed, right? It is in the same frequency, same high frequency. Now here we are introducing the LO, say I'll just call it as omega LO1, and so this is actually your mixer 1, right? Now what is happening here, this is actually shifting the center frequency to a lower center frequency, right? So there actually I am employing one more band pass filter, and that will be followed by one more mixer there. So there I'll actually introduce one more local oscillator frequency. So the idea of this multiple down conversion is a filter followed by this one, two mixers here is just to shift the center frequency in two stages. So this is omega LO2, and that will be followed by actually another filter over here. Uh, yeah, so it can be a band pass filter. If it is at the lower side, definitely it can be the channel select filter can be done using a low pass also. Let me just put up that as a band pass filter 4, right? Then this will be followed by the successive stages. Now we have actually let me put this as an intermediate frequency amplifier. So these things, depending on the frequency at which we operate, we can actually use filters accordingly. Now I will call this as mixer 2, right? Now when we try to understand the operation of each, after image reject filter you have a mixer, but I'll call that mixer as RF mixer. So what that RF mixer is doing, it is actually converting your omega in to a lower frequency, but it is not that low so that I can select the channel, right? So that is not the case here. So that is why again I am using a band pass filter here. So I will call that as channel select filter only. This is channel select filter only. But the omega IF what I am getting here is not too low, it is high. That means even the channel select filter will be having a lot of interference. So the previous stage, the previous same thing persists here. But now as we introduce a second mixer, and when we shift the local oscillator frequency to when we use another LO, we are in fact shifting this to a very low frequency. So maybe I'll call this as omega if1 and this as omega if2. Now this omega if2 is low enough so that I can actually employ a better channel selection over here, right? So this is actually the channel select filter, right? So is this clear? What I have done is I have extended this architecture with one more stage of down conversion. Right. So in a simple heterodyne receiver, the trade-off between this image rejection and channel selection is, in fact, it is very, very severe. So to resolve that, what we are doing is a simple technique of extending this heterodyning process. That is, we are employing multiple down conversion. Right. So that means what happens actually here is this technique is majorly depending on partial channel selection at progressive, like as we progress from left to right, we are doing partial channel selection even here as well as here, because we are progressively we are actually lowering the center frequencies, right? Thereby we are actually relaxing the Q requirements of both the filters, right? So the front end will select the band. After that, LNA will amplify, then followed by an image rejection filter. There we will make sure that the omega IF is large enough to reject the images properly, and then followed by the mixer where we will have we will actually translate the desired what to say, we will translate the RF frequency to a suitable intermediate frequency, and then we will do channel selection progressively at 2 stages, and thereby at the end what I have here is a proper what to say, image rejection is also done, channel selection is also done, but it is done progressively at 2 stages. All right. So let me just bring in the spectrum. Now, if I look at the spectrum, let me just get it there, and then I'll answer the questions. Okay, probably I think you can see. Let me mark the point. So the first thing what you are seeing here is actually the desired, this is actually your input, right? This is the input where this is your desired channel, and these are the interferers. I can call this as in band interferers. Then these are out of band interferers, and this is actually the image if you are looking for what to say, high side injection, right? Yes, now this is the image signal. Now when we the first stage, or let me mark the point. So this is actually at point A, probably you can see here also, this is A, and at point B what will happen is at point B this will be actually selected, right? So out of band interference will be out of band interference will not be there. We will have only this one, what is this channel, the desired channel and the in band interference, right? Now yeah, so using the filter what we use here, it is possible to eliminate some part of in out of band interference also. This is point B, followed by point C somewhere here. So after LNA, that will be little amplified. Your signal will be little amplified, and then we will have, after the first image reject filter, images can be rejected, and so this is point D. Right. So point D is after you have, all right, probably this is not shown. This is actually a C, right? So band selection is done here. Then after band pass filter, your images are actually removed to this extent, right? Then you are actually doing mixing, right? That is why this operation is shown. Actually, it has moved to a lower frequency part of the spectrum. So we have the desired signal and the in-band interference. Now there are two points where I have this is my D stage, probably this is E, F, and this is G, and say this is H. Now you can see two channel selection filter, so E and F. Uh, so E is after the first channel select filter, where in-band interference in the in-band interference strength is reduced a bit, right? Then again it is transferred to a lower frequency part through the next mixing process, and then further with the next channel select filter, the in-band interference are reduced to a very small magnitude, and finally in the intermediate frequency amplifier is used to amplify it, right? Maybe you can look at this spectrum and we can understand how channel selection is done progressively and how the interference are actually removed, right? So now let me just answer the questions. Yeah. So Rakshak, your question is Nagraj. Yes, I hope you understand that we have to use local oscillators. Actually, if you are employing two down conversion, yes, we have to do that. Now, trade off with hardware, in the sense you are yes, we need to employ one more stage of mixing, and I do understand that it's not very easy actually to incorporate one more stage, like especially something kind of a mixing. Yes, but we have to do that. Yeah. Under your question, is it not possible to eliminate all the images? Anirudh, can you make it clear? You're asking, can we eliminate image at the beginning itself, or you are asking about is it possible to eliminate the image fully?
So actually, my question is that since we're employing two mixers here, it's
Yes.
possible that there can be more than one image, right?
All right. Okay. Okay. Your question is, yeah, very good. You are, yeah, yes, you are talking. Yes, we will deal that. So there is something called as secondary image also. Yes, we have to deal with that. Yes, that is our next topic of discussion. Yes, we'll do that.
Yes.
Yeah. So yes, since we have mixers, then we have to deal with something called a secondary image. But we understand that those secondary images are located, or the channel select filter will be good enough then to take the image, take the channel itself at this point. Even though we are employing this mixer, by shifting this frequency, the secondary images are not appearing within or very close to the channel select. That we'll see. Yes, it is good, Anirudh, that you have made that point. We have to deal with secondary images also. Yes, we will see that. So apart from that, I hope it is clear from this. Now, if you look at the desired signal, you can still see that a small corruption will be there, but that will be there. Why we are showing that there is because of the filter or the way we can employ filters, right? So even if we are trying to eliminate images, it is not like 100 percentage. We can say that depending on the filter used, there can be some corruption from the image, but that is okay. Once it is within the noise floor level, those corruption are okay, or we can manage that those corruptions. Right. So this architecture where we use where we employ down conversion two times, or where we use two IF frequencies, these are called as dual down conversion or dual IF heterodyne receiver. Right. All right. So I hope it is clear. Out of 57, yes. I can I get some response? Is this clear what we discussed just now? As let me just mark at C. Now this is located at C is before shifting, right? So now this is at RF frequency, but when after shifting, it is located to the first intermediate frequency, and then it is filtered, and further it is actually moved to the second IF frequency here. This is omega IF2, right? Yeah. All right. So thank you for the responses. Now, so before looking at secondary image, before looking at the problem of the secondary image, I just want you to take to one type of receiver where we uh, So instead of employing these kind of filters, multiple down conversion, and to get a signal, instead of that, there is one architecture or there is one idea where people suggested that we can employ something called as image reject receivers itself, not by filtering, not by filtering the images, but by rejecting the images itself. So we will look at the architectures of image reject receivers, and from there we will come back to this the problem of secondary image, right? So even in a dual down conversion receiver, as Anirudh asked, secondary images will be there, but that will be definitely out of the channel select filter area. So that we will see shortly, we will see soon after this image reject receivers, right? So so the idea of image reject receiver is not use filters to remove images, rather to suppress images itself. So suppress the image without filtering the images, without filtering, that is idea. Thereby avoiding the trade-off. So we saw that there is a trade-off between this image rejection and channel selection. So we are trying to avoid the trade-off between this image rejection and channel selection. All right, yeah. So to understand this image reject receivers architecture, we need to deal with something called as the phase shift operation. So let us review certain concepts. Probably you would have dealt this in your signal system class or even in your communication system class. Let us see what is this 90-degree phase shift operation. So this is very important because this is a principle of image reject receiver. So image reject receivers do this kind of 90-degree phase shift operation. The shift by 90-degree operation is very much required in this image reject receiver. So let us understand that first. So how to understand this 90-degree phase shift operation? Say for example, I'll take a cosine wave, say a cos omega ct, which is at a frequency of omega c, angular frequency. Now I can represent this a cos omega ct as, how will I represent this? So I can write it as a, and the cos can be written in terms of this e to the power of j omega ct plus e to the power of minus j omega ct by 2. Can I represent a cos omega ct in this form? The idea is just to look at the spectrum of this. Now how do I represent the spectrum of this? So centered at omega c, you will have a impulse. Again at minus omega c, will have an impulse. If you look at the amplitude of this impulse, each will be of value a by 2. Right. So generally for a cosine signal, I can say half is the amplitude. Now I have defined the amplitude using A. So your spectrum will have two impulses at A by 2, sorry, two impulses at minus omega c and at plus omega c. Right. Now say if I want to apply 90-degree phase shift to this cosine wave. So let me write that. Apply 90-degree phase shift to this cosine wave. So if I want to do that, I will write a cos. I want to give 90-degree phase shift to this angular frequency multiplied by time. So omega ct minus 90, and that can be further written as, let me write it as a by 2 here, e to the power of j. This omega ct should be shifted by 90, and plus e to the power of minus j omega ct should be shifted by 90. This is how I can write this 90-degree phase shift operation here. Now when I simplify this further, it is nothing but you will have an a by 2 component, and this e to the power of j into minus 90 is nothing but it is minus j into e to the power of j omega ct plus, let me write it as two different components, a by 2 e to the power of minus j into minus 90, that is actually that is j component itself into e to the power of j omega ct, sorry, minus j omega ct, right. So we directly know that if you apply a 90-degree phase shift operation to a cosine wave, what you will get will be a sine wave. So I can actually I can directly write this as a sine omega ct, because we know to a cosine wave, if you apply 90-degree phase shift, it will be a sine wave, right. So how will be the spectrum differ, or how I can draw the spectrum of this? So sine wave will be having a spectrum. You have at omega c, you will have an impulse with value minus j into a by 2, and at minus omega c, we will have an impulse with an amplitude j into a by 2, right. So when I apply 90-degree phase shift to this, what I will get is a sine wave of this form, right. Now okay, let me just show in other way. Okay, so now I want to deal with see, if you look at the amplitude, you have a real amplitude here, it is a by 2, and you have you have a j component in the sine wave, right. So now I want to deal with the frequency, at what frequency, what is amplitude. You have a real amplitude and you have an imaginary amplitude. So in order to represent this, I need to go for a three-dimensional diagram, right. So because in 2D I cannot do that, because your amplitude itself is you have a real component as and an imaginary component. So what I will do here is I will represent this as I hope you are with me what I'm doing. So this is, I'll consider this as my omega axis, and say this is I'll consider my imaginary axis as this. Now I need one more axis to represent the real component, that I will take in this way, where this is my real axis, right. So probably you can visualize this as a 3D. You have x-axis, you have this frequency, then you have real component varying and an imaginary component. Yes, Rakshak, we are coming to a Hilbert Hilbert transform basically. Yes, we are coming. We are discussing to that, right. So let me just draw, let me consider this as omega c and this as minus omega c. And initially say I have a cosine signal. So cosine signal is having a real amplitude. So this is the amplitude cosine wave, right. So what is this amplitude? This is a by 2 and this is also a by 2. Now when I apply a 90-degree phase shift to this cosine wave, what happens is the component at omega c. So if you look at sine wave, I know that the amplitude is minus j into a by 2. So the component at omega c will shift from its real amplitude to an imaginary amplitude. So the value is minus j a by 2, or that means it is turning clockwise, right, 90 degree. Now the amplitude is minus j into a by 2, right. Similarly, for the component at minus omega c, it will also shift, and the value is j into a by 2, so that I can see that there is a 90-degree anti-clockwise movement towards the at the point minus omega c, right. So why I am discussing this is, now this kind of shifting, this 90-degree shifting is actually the core of your image reject receiver. So if I want to understand if the architecture of image reject receivers, I have to so how we have drawn the spectrum of a how we have drawn the spectrum of a dual conversion receiver in this way. So we will understand image reject receivers actually by drawing the spectrum points, but by plotting both the imaginary and the real component, right? So that is why we are doing this basic exercise here. Is it all right? Is it okay? Are you getting what I'm trying to do here? Okay, all right. Yeah. So basically what we are doing is we are actually doing the shift by 90° can be represented using something called as Hilbert transform, right? So for that, just to tell that, say you have, we have a sine wave. Now when you apply 90° phase shift to this, what I will get will be a class. So this will be your 90° operation. So if this is sine omega ct, this is actually a minus cos omega ct, right? That is your shift by 90°. Or just to picturize this, so what we did before is actually cosine, and to a cosine wave, what if we do a 90° operation, it will be a sine, but if you apply to sine, you will get a minus cosine. So this is 0. And this is your minus, you can consider it as a by 2. Okay, now I have taken 1, so I'll just write this as j by 2. Now your result is here. The result here is minus cosine. That means at omega c, this is minus omega c, and this is omega c. There I'll get an amplitude of minus 1 by 2. So shift by 90° is nothing but if I multiply this using this, is what happened now, right? You have a sine wave, but now if I am multiplying that using what is this function, what I have drawn here? This is what we typically call as signum function, right? But signum function with an amplitude with j. So I will write this as this shift by 90° operation. Say I'll write the, if x of t is the signal and if its transform is x of omega, now 90° operation of that can be represented as minus j signum of omega into x of omega, right? So we know what is the signum function, but when we say minus j, so this is not a signum function, this is minus j into signum function, right? Yes. So this shift by 90°, shift by 90° is nothing but we call it as Hilbert transform, right? So this, so whatever we have done is for a pure tone. Now say you have a narrowband signal, say for example you have a modulated signal, say x of t is equal to a cos, I can well represent that using omega ct plus a small shift. Now x 90° of t can be written as a sine of omega ct plus phi. Now if it is modulated, and say if I am representing using something like this, how will I picturize this on the 3D axis? This is omega, this is imaginary, and this is your real axis. Initially you have a component here at omega c and minus omega c, and this is the component, right? Now after shifting, what happens is this will become like this. So you will have an 90° clockwise movement here, and this will be like this, you have an anti-clockwise movement, right? So whatever we applied for a pure tone will be extended for modulated signals as well, right? So with this, we'll do one or two simple examples and then we will go for image reject receivers. Before that, let me ask you one question. Say you have a signal. Now if I am passing that through a block which will do Hilbert transform, but I am doing that 2 times. So what will be the output? Can I get your responses in the chat box? What form of x of omega will I get at the output? Inversion. Very good. Negation of the signal. So I'll get minus of x of omega. Very good. So that is also important here because all these things we need to understand the image reject receiver. So cascade of two 90-degree phase shift, which is nothing but Hilbert transforms, is same as negating the signal. Right. I hope whatever we have taken out, we have done now is clear for you guys. With that, I'm just giving a simple question. Plot the spectrum of A cos omega ct plus Ja sin omega ct. Just plot it. I'll ask and then you can give reply. Mayuka, are you there? Mayuka?
Yes, sir.
Okay. Are you following Mayuka, whatever we have
Yes,
done?
yes.
Okay. Okay. Yes. Likhita?
Yes, sir.
Okay. Okay. Yeah. All right. Ankita? Ankita, are you there? All right. Ankita is not there. Amritesh? All right. Amritesh is also not there. Okay. Yeah. So solve this and I'll ask and then you can actually tell me the answer. Advait Ashwin, are you there? Advait?
Yes, sir.
Okay. All right. All right. Yes, Rakshak. Yeah, you can start posting your answers here. You are getting a 0. Okay. Any other answers? Okay. A at omega c, 0 at minus omega c. Okay. So keep trying. I'll explain that here. Any more answers? A is 2, A at minus omega c, A at omega c and 0 else. Yes. Okay, others you can try. I'll just solve that here. So let me use different colors for you to have a better understanding. So let me use this color for real axis and this color for imaginary axis. All right. So now initially what I have A cos omega ct at omega c minus omega c. We'll have a component a by 2, here another component a by 2. This is my first a cos omega ct, and similarly I have j into a sin omega ct. So since it is j into a sin omega ct, okay, so a sin omega ct we know, and we have to actually multiply that. Okay, let me plot what is sin omega ct. So sin omega ct, if I want to plot an imaginary, so we saw the spectrum here before. We'll have a component here which will be of minus j a by 2, and we have another component here which is j into a by 2, right? Now what I have to do is the green color things are existing. To that we have to add a sin omega ct, which is in red, multiplied by j. So when I do multiplication with j, what happens to this term is j square will be minus 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 plus, it will be a by 2. So that will be, this component will be shifted here, and let me use a new color since it is getting transformed. So you will get something here a by 2 plus the previous a by 2, which is actually equal to a. Now here also we are doing multiplying by j square is minus, so that is actually taking us to an imaginary. All right, it is not minus, so you will be getting something called as minus a by 2, which is something like this, minus a by 2. So that will get cancelled, and your result will be, you will have at omega c, you will have a component with amplitude of a, right? So this is what a plot. So this is a just simple example where we will do this operation of 90 degree phase shift and some addition, so that we will be comfortable when we start with our image reject receivers, right? So probably we'll start image reject receivers and respective operations in next class. We'll wind up now. If you have doubts, I can take up questions.